Hi guys, our project is on accelerating car classification using a DNN on an FPGA, and I'm Matt.
I'm Nicholas.
I'm Chi.
So in order to get car classification, we first trained our model through Jupyter Notebook using the CIFAR10 dataset. This is a dataset with 10 classes, each of which are 32 by 32 images, and they are all RGB, which means they are all 3 color channels each. And we use this trained model path to get the weights for each layer that we would be using in our C++ files. So initially, the CIFAR10 modifications that we needed to do were the following. The normal data set for CIFAR10 includes 10 classes ranging from airplanes all the way to trucks. But for our classification, we only wanted automobiles and trucks. So we decided to create a data set maker that would isolate only the cars and trucks that we wanted and use that for our training and testing data set. So the one thing that we needed to keep in mind was that there are 5,000 images per class, which means that for our training set, we would have 10,000, 5,000 per car and truck, respectively. And for testing, there's 1,000 images from each. So 1,000 images of cars and 1,000 images of trucks.
So we choose a model with both convolutional layers and linear layers. At first, we were trying to do only linear layers, like multiple perception layers, but we found that the MLP model was too large, and which with only 2 convolutional layers, like in the front, we could still get a pretty decent accuracy. So we have 2 convolutional layers first, and then 3 fully connected layers after the convolutional layers. And finally, we got the train accuracy at around 90%.
The basis of our project is that we're using MLP multilayer perceptron as a mapping to basic matrix multiplication, which is a known problem in FPGAs that we already know how to do. The way this works is that the weights of the multilayer perceptron are stored as a matrix, and each row is a weight of a leading input, and each column is a weight leading into a hidden unit. All we need to do is sum all the weighted inputs together and take the dot product of the input matrix and the weight matrix. So this means we can just represent the entire thing as a series as a matrix multiplications. The only caveat being we have to implement an activation function. The activation function takes inputs and it only lets them activate or fire if input is above a certain threshold. We used RELU, which is a basic one that just zeroes out all inputs below a certain threshold. Without the activation function, the MLP is basically just a linear regression model, which is not ideal.
So on our C++ files, we needed to do a few things to optimize our initial baseline, and we decided to do some loop unrolling and some pipeline partitioning, array reshaping, loop merge, expression balancing, latency, and inlining. So the benefit of pipelining the partition basically means it can reduce the overall initiation interval of a loop or a function by allowing concurrent execution, meaning that within every n clock cycles, a new process can begin. This helps for generating a very low initiation interval design, and it can decrease the overall execution time as we can access information faster. For array reshaping, this allows us to combine array partitioning with vertical array mapping to create a new array with fewer elements but wider words, basically meaning that we can take a one-dimensional array and turn it into a two-dimensional array as an example. Though this increases hardware utilization or resources, it can decrease the execution time as you can access multiple arrays at the same time, essentially getting more information at once. For loop merging, it can merge all loops into a single loop, which can reduce the number of clock cycles at the RTL level and allow for loops to be implemented in parallel if possible. Expression balancing rearranges the operators to construct a balanced tree. This helps reduce latency, and since we're using floating point operations, we had to turn this on manually, which helped our design. And it also helped our alternative testing that we'll see in a bit. In terms of latency, this doesn't help all that much in terms of our code, but it does throw some useful warnings to help us determine where our code is causing some issues in terms of it's not able to keep up with the latency that we set it to. So our code is set to a latency of -10 nanoseconds per iteration, and this would help us determine, hey, this is not working or this is taking too long. Inletting allows for operations within a function to be shared and optimized more effectively during a function call. The caveat with this is inline functions cannot be shared or reused, and if they are called multiple times, it does increase the area and resource utilization. So that was one thing we did have to keep in mind when deciding on where to use the inline functions for conv, dense, MLP, and max pool. So in terms of I'll take this. In terms of the overall hardware resource and utilization in our results, we can see that the baseline did use less units overall compared to our alternative, which included all the optimizations. While DSP is really small, it was still an increase for the alternative, which we will see in a second.
So if we just look at the BRAM units, although we do have to use more BRAM units for our alternative design, it's not by any large factor. Next slide.
In terms of the okay, in terms of the DSP units, we do see almost a over 2 times jump in the number of units used, but it's still not enough where we are seeing any issues with the total number of DSP units that the FPGA supports.
We also have about twice as many FF units, but again, we're still not even hitting the upper bounds of the Z board's total units. The lookup table units is where we really start using a lot of the Z board, but again, we are very safe and not hitting 100% of the Z board's complete total lookup tables.
And the one comment about this lookup table massive increase is that when you're doing a lot of array reshaping, this is the direct result of that because you're changing how the arrays are structured and you do need more of them. So this is a direct result of array reshaping. And in terms of latency, we do see that overall our alternative is over 2 times faster. I think our recorded average was about 2.24, so 2.25% or times faster, which is a big increase in our design.
And if we look at the execution time for each picture, we get a 2.5 times speed up in just pure seconds, which is definitely worth any extra resources we may need to use.